This problem entails an electron moving through a cathode ray tube with an initial velocity of 7 times 10 to the 5 meters per second, while it moves through an electric field of 1.5 times 10 to the 3 newtons per coulomb. We are first asked to determine the acceleration experienced by the electron while between the parallel plates. Well, we know from mechanics that accelerations mean forces, and here the force is due to the electric field. For oppositely charged parallel plates, we know the electric field lines will point from the positive plate towards the negative plate. In other words, it's what would happen to a positive test charge if it were placed inside this electric field. However, since we have an electron in motion, it will experience a force in the opposite direction than that of the electric field. Okay, great. So mathematically, this is given as force equals charge times electric field. Don't forget that whenever we have a charged particle like an electron or a proton, we know its charge as well as its mass. So here we know Q. Calculating the result, we find that the force on the electron is equal to 2.4 times 10 to the negative 16 newtons, and it's in the positive y direction, as discussed earlier. Now that we know the magnitude of the force, we can use Newton's second law, F equals ma, because we also know the mass of the electron. Solving for the acceleration experienced by the electron, we find that it is 2.63 times 10 to the 14 meters per second squared, also in the positive y direction. I'd like to make an analogy here for what the electron experiences while it is between the two parallel plates. Imagine a ball coming off of a ledge with some initial horizontal velocity. It will fall with a parabolic trajectory due to its presence in a gravitational field. The acceleration it will experience is the acceleration due to gravity. Consider how similar this will be to what the electron experiences between the plates. In a constant electric field, it will experience a constant upwards acceleration. Coming in with a horizontal velocity, it will move upwards in a parabolic trajectory due to the acceleration caused by the electric field. As such, we will treat this problem exactly like a projectile motion problem from mechanics. Setting up a table to treat the problem as two mini problems, one in the x direction and one in the y direction, I will write down all my kinematics properties such as displacement, initial velocity, final velocity, acceleration, and time. The first thing I'll do is write down all the known values that I have from the given problem, as well as labeling any unknowns. For example, the displacement delta x, here let's call it L as that's what we're trying to find. It is important to remember that there is only acceleration in the y direction, and so the velocity in the x direction remains unchanged from its initial value. Using our kinematics equations, first we solve the mini y problem for time. Remember that both the x direction and the y direction share the same value for time, and so we can use it in the mini x problem to solve for delta x. Doing so gives a value for L of 3.19 millimeters. The next step is simply to solve for delta y1. So, referring back to our table and using our kinematics equations, we find that delta y1 is equal to 2.73 millimeters. The electron has now made it through the parallel plate electric field, and we want to find delta y2. Now that it's no longer in the electric field, the electron will no longer experience an acceleration, either in the x direction or in the y direction. As such, its final velocities, both in the x and in the y directions, when it reaches the end of the parallel plates, will remain constant until it hits the screen. This is simply another kinematics problem, and so making our two tables again, but this time with different values, we simply calculate delta y2 to be 13.7 centimeters. With this information, we now know that the total vertical deflection through which the electron moved was 13.97 centimeters. And that's it! As always, a link to a PDF version of the full solution can be found in the video description below. Thanks for watching!